Good day to you. I am Darren Chua.
And I'm Joshua Lee.
In this tutorial, we are going to look at different ways of managing multiple processors in the memory.
We will be using Lego bricks to illustrate all our examples in this video. Here, we have our main memory. The operating system is represented by the red and blue bricks. Here, we have our processors. Do note that the processors can vary in different sizes. The first method that the operating system uses is to use fixed partitions. Partitions are fixed beforehand at specific sizes to contain processors of different sizes. Once a partition size has been fixed, it will not be able to change unless the system is rebooted. In addition, each fixed partition cannot take in more than one process, even if the other process may be able to be fitted in to the unused space. This results in internal fragmentation.
In order to resolve the problem of internal fragmentation with fixed partitions, variable partitions were introduced. Partition sizes could now be fixed according to how much space the processors require. In this example, we have 3 processors. The red color process requires 40 MB, the yellow color process requires 20 MB, and the orange color process requires 20 MB. Since the red color process requires 40 MB of space to run, the memory allocates 40 MB partition space for the red color process. The yellow color process and the orange color process are also given 20 MB of partition space each. Therefore, variable partitions are better compared to fixed partitions as it does not waste much unnecessary space. On top of that, variable partitions have another added advantage in which unused spaces beside each other, also known as a contiguous block, can be merged to run another process of a larger size. In this example, the yellow colored process and orange colored process of each 20 MB are beside each other and ended simultaneously. These 2 blocks of space can be merged together to run another process, in this case the blue colored process, which is 40 MB. However, this solution is still not foolproof because it may result in external fragmentation. What if the unused spaces were not beside each other? Then, it cannot be merged to run another process of a larger size. This may leave behind unused spaces. In this example, we have a 10 MB and a 40 MB empty space. The green colored process, which requires 50 MB, is unable to fit in, and these 2 blocks of empty space are also not able to merge together. This results in external fragmentation. Now that all the examples have been illustrated, it is obvious that the problem is that our entire program needs to be stored in the main memory at contiguous locations, resulting in external fragmentation. Therefore, we need to separate the processors into smaller chunks to remove the restrictions. The first way to do so was paging. Each incoming job is divided into pages of equal sizes. The memory manager determines how many pages are in the program. Then, it loads them into memory locations known as page frames. The advantage is that jobs can be allocated in non-contiguous memory locations, so that memory is used more efficiently. However, the disadvantage is that internal fragmentation may occur on the last page. In order to resolve the problem faced by paging, demand paging was introduced. The demand paging is a modified version of paging. We have 2 boards here, and one of the board represents the pages of the red colored process that are not required at the moment. The other board represents pages that are required to be loaded into the memory. The pages that are required to be loaded into the memory will be transported to this board, and then it will be loaded on demand into the memory. The advantage is that the jobs are no longer constrained by the size of the physical memory and utilizes the memory more efficiently. The disadvantage is that the page map table can actually cause increased overheads.
In order to remove internal fragmentation faced by demand paging, segmented memory allocation was introduced. Each incoming job is divided into several segments of different sizes. The main memory is now allocated dynamically instead of being divided into page frames. Segments are numbered and loaded into the memory only when they are needed. The advantage is that internal fragmentation is removed. The disadvantages are that variable length segments are difficult to manage and external fragmentation also occurs. In order to remove external fragmentation faced by segmented memory allocation, segmented demand paging was introduced. This combines the benefits of both methods into a single method of memory allocation. The segments are subdivided into pages of equal sizes and makes it easier to manipulate and handle. Therefore, the memory now contains different sized segments and pages within the segments. The problems of segmentation, which are compaction and external fragmentation, are removed as pages are of fixed length. This scheme, however, requires a job table, segment map table, page map table, and memory map table. In conclusion, there are two initial ways, fixed and variable partitions, and four better ways, paging, demand paging, segmented, and segmented demand paging. The best way of managing multiple processes in the memory is to use segmented demand paging. Although it may involve more tables, it makes full use of the memory space and solves problems of internal and external fragmentation. That's the end of this video. Thank you for watching.